Welcome to the Hypnos Sleep Channel and settle in for an extraordinary journey through deep space with Hypnos, the ancient Greek god of sleep, as he guides us gently toward one of the most misunderstood objects in the universe, the black hole. For now, imagine leaving Earth far behind. The noise of the day falls away. The lights of cities become a soft pattern on a small blue world. Then a point. Then only memory. Ahead of you is the deep quiet between stars, and somewhere in that darkness waits a place where light, time, and motion no longer behave in the ordinary way. You are not falling yet. You are drifting at a safe distance, looking toward a region where there should be something visible, a star, a planet, a surface, an edge. But there is no surface waiting in the dark, no shell, no crust, no glowing wall. So what would you actually see if the thing in front of you gives off no light? You would see its influence. The stars behind it would not look quite right. Their light would bend around the unseen center, as if space itself were acting like a lens. The darkness would not announce itself by shining. It would announce itself by changing the paths of everything around it. What you are facing is stranger than an object. It is a region where the shape of space-time has changed so deeply that every possible path outward can eventually fail. This is what makes a black hole a black hole. Light can still move at light speed. Matter can still fall, orbit, heat, and radiate. Signals can still travel locally as they should. But beyond a certain boundary, all future paths point inward. That boundary is called the event horizon. It is not made of matter. It is not a physical surface. If you could approach it in an imaginary ship, you would not see a metal rim or a dark wall waiting to strike you. The event horizon is a line in the structure of space-time itself. Outside it, the universe can still receive messages from you. Inside it, no signal can ever return. But why would a boundary like that exist at all? Why would there be a place where escape stops being possible, even for light? To answer that, we have to ask a quieter question. What is gravity, really? In everyday life, gravity feels like a pull. A stone drops from your hand. The moon circles Earth. Earth moves around the sun. It is natural to picture an invisible force reaching across space. But in Einstein's general relativity, gravity is something deeper. Matter and energy curve space-time, and objects moving freely follow those curves. If you could see that geometry around the sun, Earth would not look like a ball being dragged by a rope. It would look like a traveler following a path through curved space-time. The sun shapes the stage, and Earth moves along the stage's geometry. The same idea works near Earth, around stars, and in its most extreme form, around a black hole. This is not only a beautiful idea, it is measurable. Clocks tick at slightly different rates depending on gravity. Light bends when it passes near massive objects. The orbit of Mercury shifts in a way Newton's theory could not fully explain. General relativity changed gravity from a simple attraction into the structure of the arena where motion happens. Now imagine that the journey carries your attention inward. A great amount of mass is being compressed into a smaller and smaller region. What happens to the geometry as all that mass is squeezed tighter? the curvature around it steepens. Paths that once curved gently begin to tilt inward more severely. At a certain radius, escape would require moving faster than light. Since light speed is the cosmic speed limit, that radius becomes one way. Outside it, some paths can still lead back to the wider universe. Inside it, none do. For a non-rotating black hole, this boundary is described by the Schwarzschild radius. The rule is beautifully simple. More mass means a larger horizon. Double the mass, and the radius doubles. If the sun could somehow be compressed into a black hole without changing its mass, its event horizon would be only a few kilometers across. Earth would need to be squeezed to about the size of a small coin. The point is not that such objects form this way. The point is that black holes reveal what can happen when enough mass is packed into a small enough space. This is also where one of the most common myths falls away. If black holes are so extreme, why do we say they are not cosmic vacuum cleaners? Because from far away, a black hole's gravity behaves like the gravity of any other object with the same mass. If the sun were replaced by a black hole of exactly the same mass, Earth would not suddenly be pulled inward. It would continue orbiting almost as before. The sunlight would vanish, and the world would change in every living way. But the orbit itself would not collapse simply because the sun had become a black hole. The real danger is not magical suction. The danger is closeness. If your imaginary ship moved nearer and nearer to the horizon, the map of possible futures would begin to narrow. Far away, there are many directions you can travel. Near the horizon, fewer paths lead safely outward. At the boundary, escape stops being difficult and becomes impossible. Not because something grabs you, but because space-time no longer offers an outward route. So, as you hover in thought near this invisible edge, the black hole becomes less like a monster in space and more like a revelation about space itself. It does not need to reach for you. It only needs to curve the road. The closer we look, the less it resembles a simple hole, and the more it becomes a quiet lesson about what gravity really is. Now let the journey carry you backward, away from the quiet horizon, to the place where many black holes begin. Imagine approaching a star far larger than the sun. From the outside, it may look stable, a blue-white furnace pouring light into the surrounding gas. But what is holding that enormous object up? Inside the star, two forces are locked in balance. Gravity pulls inward, trying to crush everything toward the center. Fusion releases energy in the core, creating pressure that pushes outward. For millions of years, those two tendencies can hold each other in a kind of luminous agreement. The star shines because the balance is working. But the balance is not permanent. The more massive a star is, the hotter and denser its core becomes, and the faster its nuclear reactions proceed. This is one of the strange lessons of stellar life. The biggest stars do not live the longest. They spend their fuel extravagantly, shining with immense power while racing toward an ending that smaller stars may avoid for billions of years. If you could look inside the giant, you would not find a simple ball of fire. You would find layers. At first, hydrogen fuses into helium. Later, if the star is massive enough, helium fusion gives way to heavier stages. Carbon, neon, oxygen, and silicon can burn in sequence, each stage requiring higher temperatures and building new shells around the core. The interior begins to resemble an onion, but this is not a quiet structure. It is pressure, heat, radiation, and nuclear transformation arranged by gravity. And here is where the clock begins to tighten. Hydrogen burning may continue for millions of years. Helium burning is shorter. Carbon and oxygen burning are shorter still. By the time silicon begins building iron group elements, the final stage can be measured in days. A star that seemed eternal from a distance is approaching a failure faster than a human conversation. Why does iron change the story? For most of the star's life, fusion releases energy. Lighter nuclei combine, and a small amount of mass becomes energy that helps support the star against collapse. Iron sits near the peak of nuclear binding energy. Fusing it into heavier elements does not release useful support in the same way. It costs energy instead. Once enough iron gathers in the center, the furnace has reached a dead end. Now imagine the core at that moment. The outer layers are still pressing inward with immense weight, but the center can no longer answer with enough pressure. Gravity does not pause politely. Collapse begins deep inside. Matter that once filled a region thousands of kilometers across falls inward at a significant fraction of the speed of light. Atoms are forced beyond their familiar architecture. Electrons are driven into protons, producing neutrons and neutrinos. What happens next depends on how much mass remains. In many cases, the core rebounds and helps launch a supernova, blasting the outer layers into space. If the remnant is not massive enough to keep collapsing, a neutron star may form, a city-sized object with a physical surface. But if the remaining core crosses the limit where known pressures can resist gravity, there is no stable surface left. The collapse continues and the forming object passes inside its own event horizon. That distinction is important. A neutron star is already extreme, but it can still send light from a surface. A black hole is what happens when even that resistance fails. The material does not vanish from the universe. Its mass, spin, and gravitational influence remain. But the details of what fell inward become hidden behind a causal boundary. So the death of a massive star is not only an explosion, it is a change in how the universe can know what happened. The outer layers may scatter elements into space, enriching future stars and planets. The collapsed center may become a horizon. A bright stellar life becomes a story told not by light from the surface, but by gravity around an invisible remnant. As you move away from the remains of the dying star, the next question is one of scale. Are all black holes roughly the same kind of object, or does size change the experience? Mass changes almost everything. How a black hole forms, how it behaves, how it is detected, and what it does to the space around it. The smallest confirmed population in ordinary astronomy is made of stellar mass black holes. These are usually the remnants of massive stars, with masses ranging from a few to many times the mass of the Sun. Imagine one of them alone in the darkness. If nothing nearby feeds it, it may be almost invisible. It has no glowing surface. It may pass through the galaxy as a compact gravitational shadow, known only if its gravity bends light or disturbs the motion of something else. But place that same kind of remnant near a companion star, and the scene changes. Gas can be pulled away, heated, and made to shine before it ever reaches the horizon. Stellar mass black holes matter because they connect black hole physics to the life cycles of stars. They can be solitary, hidden companions, X-ray sources, or members of pairs that eventually merge. Many of the black holes detected through gravitational waves belong to this broad family. They are not theoretical curiosities. They are part of stellar evolution. Now imagine widening the scale. Between stellar remnants and galactic giants lies the harder category of intermediate mass black holes. What would such an object look like? Not bright enough to announce itself like a quasar, not common enough to reveal itself easily in nearby binaries. These candidates may contain hundreds, thousands, or tens of thousands of solar masses. Astronomers search for them in dense star clusters, unusual X-ray sources, and merger signals that may reveal objects heavier than ordinary stellar collapse would usually produce. Then the journey carries you outward to the centers of galaxies. There, the scale becomes almost difficult to hold in the mind. Supermassive black holes contain millions or billions of solar masses. Our own Milky Way contains Sagittarius, a star, often shortened to Sagittarius A star, with a mass of about 4 million suns. The galaxy Messier 87 contains M87 star, a much larger object of about 6.5 billion solar masses. These are not enlarged planets or oversized stars. They are horizons on galactic scales. Here is the surprising part. A larger black hole does not always mean a more violent horizon. The average density inside the horizon can be lower for a larger black hole because the horizon radius grows in direct proportion to mass, while the volume inside that radius grows much faster. This does not make it safe. It means scale changes how gravity is experienced near the boundary. A supermassive horizon can spread tidal effects across a greater distance. Scientists also discuss primordial black holes, but this idea must be handled carefully. If such objects exist, they would not have formed from dying stars. They would have come from dense regions in the early universe. Primordial black holes remain a serious research idea, especially in cosmology and dark matter discussions, but they have not been confirmed. The word matters, hypothetical. So the map becomes clearer. Stellar mass black holes are tied to the deaths of massive stars. Intermediate mass black holes may help bridge the gap between stellar remnants and galactic centers. Supermassive black holes anchor galaxies and can influence enormous environments. Primordial black holes, if they exist, would belong to the earliest cosmic chapters. These categories are not just labels. They change what you would notice as an observer. A small black hole may reveal itself by stealing matter from a nearby star or merging with another compact object. A supermassive one may reveal itself through orbiting stars, glowing accretion disks, relativistic jets, or the shadow structure imaged by Earth-sized telescope networks. The same basic idea, an event horizon, can appear as a hidden remnant, a gravitational wave source, or a central engine powerful enough to affect a galaxy. That is one of the deep patterns in black hole astronomy. The horizon itself is simple. The surroundings are not. Around the same dark boundary, the universe can create X-rays, jets, warped light, disrupted stars, ripples in space-time, and luminous galactic cores. A black hole may be defined by what cannot escape, but it is often discovered through everything that still can. Now imagine approaching a black hole that is not alone. From far away, you might expect darkness because the horizon itself emits no ordinary visible light. But as the scene sharpens, you see something unexpected, a glow around the dark center, sometimes brighter than stars. How can an object famous for trapping light power so much brilliance? The answer begins before matter crosses the horizon. Gas falling toward a black hole usually does not drop straight in. It already has sideways motion because it came from an orbiting star, a turbulent cloud, or a rotating galactic environment. As it moves inward, that sideways motion makes the material gather into a flattened, rotating accretion disk. If you could hover safely above that disk, it would not look like a solid plate. It would be hot plasma threaded by magnetic fields, stirred by turbulence, and heated by friction-like processes as inner regions orbit faster than outer regions. The disk glows because gravitational energy is being converted into heat and radiation before the matter disappears from view. This is why a dark horizon can be surrounded by light. In some systems, the disk shines in visible light, ultraviolet light, and X-rays. Near stellar mass black holes in binary systems, this glow can reveal an otherwise invisible companion. Near supermassive black holes, accretion can become powerful enough to light the center of an entire galaxy. Quasars are the extreme example. Imagine looking across billions of light years and seeing a galactic core shining with extraordinary power. The central black hole itself remains dark, but the infalling gas can radiate with astonishing intensity. Some of the brightest objects in the universe are powered by objects famous for not letting light escape. The darkness is real, and so is the brilliance around it. This corrects a common misunderstanding. A black hole does not need to shine to dominate a scene. It can make other materials shine by forcing it into extreme motion. Gas in an accretion disk is not simply falling. It is orbiting, colliding, heating, stretching, and losing energy. The disk becomes a visible record of gravity doing work. Now look above and below the disk. In some systems, narrow jets shoot outward from regions close to the poles of the accretion flow, carrying particles at nearly the speed of light. This sounds as if matter is escaping from the black hole, but that is not what is happening. Once matter crosses the event horizon, it cannot return. Jets are launched outside the horizon in the complex environment of magnetic fields, rotating plasma, and in many cases, black hole spin. A lighthouse can help us picture direction, but only carefully. A lighthouse has a lamp and a lens. A black hole jet is a physical beam of energized particles and radiation shaped by magnetic fields and motion. The comparison helps with orientation, not with the engine. The engine is astrophysical. In large galaxies, these jets can extend thousands or even millions of light years. They can inflate bubbles in surrounding gas, heat the environment, and affect future star formation. This is one way a central black hole, tiny compared with its host galaxy, can still influence regions far beyond its horizon. A boundary smaller than a solar system in cosmic terms can help shape gas across galactic distances. So when you picture a black hole, Do not imagine only emptiness. Imagine a system. At the center is the event horizon, dark and one way. Around it may be a disk brighter than stars, magnetic fields twisted by motion, jets reaching across space, and radiation carrying news of the invisible center. The black hole hides itself, but the universe around it becomes a kind of announcement. Now imagine standing beside a planet-sized instrument, not one telescope, but many radio observatories spread across Earth. Each dish is turned toward a target so distant and so small on the sky that ordinary photography would fail. The question is simple to ask and almost impossible to answer. What would a black hole actually look like? The most famous modern answers came from the Event Horizon Telescope, or EHT. In 2019, the collaboration released an image of the shadow of M87 star. In 2022, it released an image of Sagittarius A star, the supermassive black hole at the center of the Milky Way. These images changed public imagination, but they require careful language. They are not ordinary photographs of a solid surface. They are not direct pictures of the event horizon itself. What you are seeing is radio emission from hot material near the black hole, shaped by extreme gravity with a dark central region known as the shadow. That shadow is connected to the horizon, but it is larger than the horizon because it includes the behavior of light captured or bent by curved space-time. How could telescopes on Earth see something so tiny? The EHT uses very long baseline interferometry, linking radio observatories across the planet. By combining signals from distant telescopes, scientists create the resolving power of an Earth-sized instrument. This is necessary because black hole shadows are incredibly small on the sky. Even a supermassive black hole can appear smaller than an orange on the moon would appear from Earth. Now place two targets in your imagination. M87 star is about 55 million light-years away. That distance is staggering. Yet its mass is so enormous, about 6.5 billion suns, that its shadow is large enough in apparent size for the EHT to resolve. Sagittarius. A star is much closer, about 27,000 light-years away, but it is far less massive. The gas around it changes in minutes, which makes imaging harder. It is like trying to take a long exposure of something that keeps changing its expression. What is the glowing ring teaching us? It is a lesson in gravitational lensing. Light does not always travel along the straight paths our everyday intuition expects. Near a black hole, space-time is curved so strongly that light from behind the object can bend around and reach us. Radiation from the far side of an accretion disk can appear above, below, or around the dark center. Some photons can circle close to the black hole before escaping toward Earth. The dark center is not simply the silhouette of a solid object. It is the region where light paths are captured or redirected away from the observer. The shadow is therefore a visual consequence of both the horizon and the curved geometry around it. What we see is not just matter. We see the rules of motion made visible. If one side of the ring looks brighter, that is not necessarily because the disk contains more material there. Motion itself can change brightness. If part of the emitting gas is moving toward us, Doppler beaming can make it appear brighter. If another part is moving away, it can appear dimmer. The image contains heat, motion, gravity, and perspective all at once. This is why the EHT images matter so much. They did not merely produce dramatic pictures. They tested whether the size and shape of the observed ring matched predictions from black hole models. For M87 star, the ring was consistent with general relativity. For Sagittarius, a star, the image strengthened the case that the compact object at the Milky Way's center is a black hole. The quiet wonder is that the image is not a picture of darkness alone. It is a picture of light losing the argument with gravity. Around the unseen center, photons curve, loop, brighten, fade, and disappear. The black hole remains hidden, but its absence has a shape. But suppose there is no glowing ring to photograph. Suppose the black hole is quiet, dark, and alone. How would anyone know it is there? Astronomers do not need to see a horizon directly to measure its influence. For most of the history of the subject, black holes were detected indirectly. They were known through what they did to stars, gas, light, and space-time itself. The invisible becomes measurable when it changes the motion of something visible. One method is orbital motion. Imagine watching a star circle a place where no star can be seen. If astronomers measure that orbit, they can estimate the hidden mass. If the unseen object is too massive and too compact to be a normal star, a white dwarf, or a neutron star, a black hole becomes the best explanation. In X-ray binaries, a black hole can pull gas from a companion star. As the gas forms a hot accretion disk, it emits X-rays that reveal the system. Another method is stellar motion near galactic centers. At the center of the Milky Way, individual stars have been tracked for years as they move around an invisible central mass. Some pass extremely close to Sagittarius, a star, and swing around at high speeds. Their orbits show that about 4 million solar masses are packed into a small region. A cluster of ordinary faint stars could not easily remain so compact without revealing itself or dispersing. The simplest explanation is a supermassive black hole. Light itself can also expose a dark object. If a compact mass passes in front of a background star from our point of view, its gravity can bend and magnify the star's light. The black hole remains dark, but the background light changes. It becomes visible through distortion, as if the unseen mass briefly turned space into a lens. Accretion provides another signal. Hot gas near a black hole can radiate across the electromagnetic spectrum. Radio waves may trace jets. Infrared light may reveal dust and stars near a galactic center. Optical and ultraviolet light may come from active galactic nuclei. X-rays can emerge from the hottest inner disk regions around compact objects. Each wavelength is a different messenger from the environment around the horizon. Then there are gravitational waves. Imagine two black holes orbiting one another in complete darkness, with no glowing disk and no visible explosion. Their motion can still shake space-time. When they merge, they produce ripples that travel outward at light speed. These waves do not require photons. They come from the motion of the black holes themselves, and detectors on Earth can measure the tiny stretching and squeezing they cause. This is one of the great changes in modern astronomy. For centuries, astronomy was almost entirely the study of light. Telescopes collected visible light, then radio waves, infrared, ultraviolet, X-rays, and gamma rays. Gravitational wave detectors added a new sense. Instead of seeing photons, we measure changes in distance caused by ripples in space-time. Black holes became not only objects we infer, but objects we can hear in the geometry of the universe. Every method has limits. An X-ray source may be confusing. A lensing event may require careful modeling. A gravitational wave signal may not come with a visible counterpart. An EHT image requires extraordinary resolution. But together, the methods reinforce one another. They show black holes as real astrophysical systems, not just mathematical possibilities. That is important because black holes began as solutions to equations. For a long time, they seemed almost too strange to belong to nature. Now we have measured their masses, watched stars orbit them, imaged their shadows, detected their mergers, and studied the matter that glows around them. A black hole does not need to send light from its horizon to be known. It can bend the light of others, make gas shine, command stars, and shake space-time. Now let the journey turn toward home, not all the way back to Earth, but toward the center of our own galaxy. Sagittarius. A star is the supermassive black hole at the heart of the Milky Way. It is not close in human terms. It lies about 27,000 light-years away, hidden behind dust, stars, and gas toward the constellation Sagittarius. But on the scale of galaxies, it is our local example. If you could look through the dust and watch the inner Milky Way over many years, you would see stars moving around an invisible center. Some of these stars trace tight, fast orbits. They swing around a point where no ordinary luminous object appears. What question does that motion raise? What kind of unseen mass could guide stars so precisely? The answer comes from the orbits. Sagittarius. A star has a mass of about 4 million suns. That sounds enormous, and it is, but compared with the giants in some other galaxies, it is modest. M87 star is more than 1,000 times more massive. Still, 4 million suns confined to the center of our galaxy is far beyond anything ordinary stellar physics can explain. The evidence for Sagittarius. A star is especially strong because astronomers have watched individual stars orbit it. Their paths reveal not only mass, but concentration. The central object must be extraordinarily dense and compact. A cluster of ordinary faint stars could not remain packed there without revealing itself or dispersing. The best explanation is a black hole. The EHT image of Sagittarius. A star added a different kind of evidence. It showed a ring-like structure consistent with hot emission around a black hole's shadow. This was not easy. Because Sagittarius, a star, is much less massive than M87 star, the gas near it orbits and changes quickly. During the time it takes to gather data, the source can vary. Scientists had to reconstruct an image from a changing target. That difference teaches scale. Around a smaller supermassive black hole, the characteristic times are shorter. Near a larger one, the same processes unfold more slowly. M87 star is much farther away, but its enormous mass makes the near-horizon environment change more gradually. Sagittarius. A star is closer, but more restless. One is distant and massive. The other is local and lively. Our galaxy's central black hole is also relatively quiet compared with a quasar. It is not currently feeding at a rate that makes the Milky Way blaze as an active galaxy. But quiet does not mean inactive. It can flare, interact with gas, and shape the inner galactic environment. A black hole can be dormant in one era and active in another, depending on the supply of surrounding matter. The stars near Sagittarius. A star are useful clocks and test particles. Their orbits allow astronomers to study gravity in a strong field environment. When a star passes close to the central mass, its light and motion can reveal relativistic effects. The center of the Milky Way becomes a natural laboratory, not because we can visit it, but because gravity has arranged bright markers around a dark center. There is something quietly powerful about this. The black hole at the heart of our galaxy is not an object we notice in the night sky with unaided eyes. It does not hang overhead as a visible disk. It is hidden behind distance and dust. Yet its presence is written into the motion of stars. The center is dark, but the stars around it have been keeping records for years. Sagittarius. A star reminds us that black holes are not only distant curiosities. One sits in the middle of our own galactic home. It is not a threat to Earth at our distance. It is not dragging the solar system inward. It is part of the Milky Way's architecture, a compact central mass surrounded by stars, gas, magnetic fields, and history. Now imagine turning from our own galactic center toward a far larger system, tens of millions of light years away. M87 star sits at the center of the giant elliptical galaxy, Messier 87. Its mass is about 6.5 billion times the mass of the Sun, making it one of the great anchors of modern black hole astronomy. Why did this distant object become the first black hole shadow ever imaged? The answer is scale. Although M87 star is vastly farther away than Sagittarius A star, it is also vastly more massive. Its shadow is large enough on the sky for the Event Horizon Telescope to resolve. This creates a remarkable scale paradox. A black hole in another galaxy can appear comparable in angular size to the one at the center of our own because mass and distance are competing in the observation. The 2019 EHT image showed a bright ring surrounding a dark central region, consistent with predictions from general relativity. It did not show the horizon as a surface. It showed emission from hot material near the black hole, bent and shaped by the surrounding geometry. The shadow gave the invisible a measurable outline. Messier 87 is also known for its jet. If you could see the galaxy in the right wavelengths, a narrow beam of energetic particles would appear extending from the center across thousands of light years. What could launch something so vast from a region so small? The jet is connected to the environment outside the horizon: accretion, magnetic fields, rotating plasma, and likely black hole spin. Again, the material in the jet is not escaping from inside the event horizon. It is launched from outside, where the surrounding engine is still visible to the universe. This helps explain why supermassive black holes matter to galaxies. The horizon itself may be tiny compared with the galaxy, but the energy released near it can travel outward. Jets and outflows can heat gas, carve cavities, and affect the conditions for star formation. The details are complex, and no single sentence explains every galaxy. But Messier 87 demonstrates that the region around a black hole can influence matter on a scale far beyond the horizon. The ring image of M87 star also tested a deep prediction. General relativity says that a black hole of a certain mass should produce a shadow of a certain size. The observed ring was consistent with that expectation. This does not mean every question is answered. Plasma physics near the black hole is difficult. Magnetic fields, turbulence, and radiation all complicate the scene. But the broad agreement between theory and observation was a remarkable success. Think about what had to happen for that image to exist. Radio waves left a region near a black hole in another galaxy. They traveled for tens of millions of years. They reached Earth, where observatories across the planet recorded them with extraordinary precision. Atomic clocks, data storage, calibration, supercomputing, and global collaboration turned those signals into an image. That image was not only a picture of a distant object, it was a demonstration of human patience. M87 star is not a nearby companion in the Milky Way. It is a cosmic landmark, a distant engine, a test of gravity, and a reminder that black holes can be central to the lives of galaxies. Its shadow shows the boundary where light is lost. Its jet shows energy moving outward from the region around darkness. Together, they reveal the two sides of black hole astronomy, the hidden center and the surrounding universe where the consequences shine. Now imagine moving closer again, not crossing the boundary, but watching from a safe distance as a small probe falls toward the horizon. What would you actually see? The first strange effect is time. This is not a metaphor. In general relativity, time is part of space-time, and space-time is shaped by matter and energy. A clock deeper in a gravitational field ticks more slowly relative to a clock far away. Near Earth, the effect is tiny but measurable. Near a black hole, it becomes dramatic. As the probe approaches the event horizon, signals from it take longer to climb out. Its light loses energy and shifts toward redder wavelengths. The signal becomes dimmer and more delayed. From far away, the fall appears to slow near the boundary. The outside observer never receives a simple final image of the object crossing. But what would the probe experience? From its own point of view, the story is different. It can cross the horizon in a finite amount of its own time. The event horizon is not necessarily a place where something local and violent happens at that instant, especially for a very large black hole. There may be no solid surface, no impact, no glowing line in space. The crossing is dramatic because of what it means causally. Afterward, every future directed path leads deeper inward. This difference between viewpoints is one of the most important ideas in relativity. Time is not a single universal river flowing at the same rate everywhere. Observers moving along different paths through curved space-time can describe the same event differently. The distant observer sees fading, reddening, and delay. The falling object experiences continued motion. Both descriptions belong to the same geometry. Why does the light turn red? A photon escaping from near a black hole loses energy as it climbs away from strong gravity, and lower energy light has a longer wavelength. This is gravitational redshift. It is not caused by the photon rubbing against space or losing energy to air. It is a consequence of climbing out of curved space-time. The deeper the photon begins, the more redshifted it can become before reaching a distant observer. Near the horizon, paths for light become profoundly altered. Some light can escape. Some can orbit temporarily in unstable paths. Some falls inward and never reaches the outside universe. This is why black hole images are not simple pictures of surfaces. The geometry decides which photons arrive, which are delayed, which are bent around, and which are lost. If the black hole is surrounded by an accretion disk, the scene becomes even stranger. The far side of the disk can curve into view. The underside may appear above the black hole. Motion can brighten the approaching side. Time delays can make different parts of the disk appear at subtly different moments. What looks like a glowing ring is really a map of possible paths through curved space-time. The event horizon itself remains a boundary of no return. It is not a fire, not a shell, not a crust, and not a place where ordinary material piles up like dust on a floor. It is defined by causal structure. Outside it, some future paths can still lead away. Inside it, none do. The closer we get in thought, the more the black hole becomes less like an object and more like a change in what futures are available. Time stretches. Light reddens. Paths bend. Signals fade. The horizon does not need to reach out. It only marks the place where outward becomes impossible. Now imagine the danger becoming physical. Until now, the horizon has been a boundary of information and possible paths. But if you move close enough to a black hole, gravity does not pull on every part of an object equally. What happens when one side of you is closer than the other? That difference is called a tidal force. On Earth, the moon's gravity pulls slightly differently on different parts of our planet, helping raise ocean tides. Near a black hole, the same idea can become extreme. The side of an object closer to the black hole feels a stronger pull than the side farther away. Imagine falling feet first toward a stellar mass black hole. Your feet are closer than your head, so they feel a stronger gravitational pull. The difference stretches you along the direction of falling and compresses you sideways. This process is often called spaghettification. The name sounds almost playful, but the physics is severe. It is tidal gravity overwhelming the strength of an object. Does a larger black hole always mean a worse horizon? Surprisingly, no. The strength of tidal forces depends not only on mass, but also on distance and scale. A supermassive black hole can have weaker tidal forces at its event horizon than a stellar mass black hole. Bigger does not automatically mean more destructive at the boundary. A supermassive black hole has a much larger horizon, so the change in gravity across a human-sized object at that location can be smaller. This does not make a supermassive black hole safe. It means the danger is distributed differently. You might cross the horizon of a very large black hole without being torn apart at that exact boundary, but deeper inside, tidal forces would continue to grow. The horizon marks the point of no return, not necessarily the point where destruction happens immediately. This distinction corrects a common picture. Many people imagine the horizon as the most violent place. For small black holes, the region near the horizon may indeed involve devastating tidal forces. For very large ones, the boundary can be locally less dramatic. The real terror is not always a sudden surface event. It is the certainty of the future path after crossing. Inside the horizon, classical general relativity predicts continued motion inward toward a singularity, or toward a region where the theory itself reaches its limit. That word, singularity, must be used carefully. It does not mean we fully understand what physically exists at the center. It means the equations, as written, produce infinities or break down. A singularity is not a neat object waiting to be photographed. It is a warning sign from the theory. Most physicists expect that a full description of the deepest interior would require quantum gravity, a theory that successfully combines general relativity with quantum mechanics. We do not yet have a complete experimentally confirmed version of that theory. So the honest statement is this: classical relativity predicts an interior where collapse continues beyond the horizon, but the final description of the deepest region remains an open problem. The journey inward therefore teaches both knowledge and humility. We can describe time dilation, redshift, tidal forces, and the causal meaning of the horizon with great confidence. We can calculate how outside and falling observers differ. We can predict many features of the space-time. But at the deepest center, our theories signal that something is unfinished. That is one reason black holes remain so important. They are not just strange objects in space. They are places where our most successful theories are pushed until they reveal their limits. The event horizon hides the interior from outside observers. But the questions raised by that hidden region reach far beyond the black hole itself. Now imagine that the black hole is not still. In the real universe, most black holes are expected to rotate. Why should that matter? Because in general relativity, rotation can change not only the motion of nearby matter, but the surrounding space-time itself. A non-rotating black hole is the cleanest starting point for understanding horizons, but nature rarely provides perfectly still objects. Stars rotate. Gas clouds rotate. Binary systems orbit. When matter collapses, some of that angular momentum can remain. In classical general relativity, a rotating black hole is described by the Kerr solution. A Kerr black hole is not simply a Schwarzschild black hole spinning like a solid ball. It has no solid surface doing the spinning. The geometry itself is different. Around a rotating black hole, space-time is dragged in the direction of the spin. This effect is called frame dragging. If you could place markers in the empty space nearby, they would not remain perfectly independent of the rotation. Near a rotating black hole, space and time are not passive emptiness. They are part of the gravitational field. When the central object rotates, nearby inertial frames are pulled around with it. In plain language, the black hole makes the surrounding space-time participate in its rotation. One region created by rotation is the ergosphere. It lies outside the event horizon of a rotating black hole. What would be strange about entering it? Inside the ergosphere, no object can remain perfectly stationary relative to distant space. Everything must move with the dragged space-time to some degree. The horizon is still the point of no return, but the ergosphere is a surrounding region where rotation becomes unavoidable. This rotating region creates a remarkable possibility. In principle, energy can be extracted from a rotating black hole. The Penrose process is a theoretical mechanism in which a particle entering the ergosphere splits, with one part falling in and the other escaping with more energy than the original particle had from the outside perspective. The extra energy comes from the black hole's rotation. In real astrophysical systems, magnetic fields and plasma processes may also tap rotational energy. This is one reason spin is connected to jets and active galactic nuclei. The details are complex, but the larger idea is clear. A black hole is not only a sink. Under the right conditions, the region around it can act as an engine. A figure skater pulling in their arms can help explain angular momentum, but the analogy has limits. A black hole is not a skater and not a solid sphere with a surface. The useful idea is that rotating matter can keep angular momentum as it collapses into a smaller region. In a black hole, that rotation becomes part of the space-time geometry outside the horizon. Spin also affects where stable orbits can exist. Around a rotating black hole, matter can orbit closer in one direction than another, depending on whether it moves with or against the spin. This changes the inner edge of the accretion disk and influences how efficiently gravitational energy can become radiation. The glow around a black hole is therefore shaped not only by mass, but also by rotation. This adds another layer to black hole simplicity. From far outside, a settled black hole can be described by only a few properties, especially mass and spin, with charge usually expected to be negligible in astrophysical environments. Yet those few properties create rich effects. Mass curves space-time. Spin drags it. Together they shape disks, jets, shadows, orbits, and gravitational waves. Now imagine two black holes instead of one. They may begin far apart, orbiting slowly in darkness, with no glowing disk and no visible surface. If no telescope can see them, what carries the news of their motion across the universe? The answer is gravitational waves. These are ripples in space-time produced by accelerating masses. They are not sound waves moving through air, and they are not light waves moving through electromagnetic fields. They are changes in the geometry of space-time itself, traveling outward at the speed of light. Any accelerating mass can produce them in principle, but only the most extreme systems create waves strong enough for us to detect across cosmic distances. A pair of orbiting black holes is an ideal source. As the objects circle each other, they disturb space-time. Energy leaves the system in the form of gravitational waves, causing the orbit to shrink. As the black holes move closer, they orbit faster. As they orbit faster, they radiate more strongly. The process accelerates toward a final merger. What happens in the last moments? Two horizons approach, distort, and combine into one. The new black hole is not immediately calm. It settles through a phase called ring-down, like a struck bell returning to stillness. But this ringing is not sound in air. It is the shape of space-time relaxing after an extreme disturbance. In 2015, LIGO made the first direct detection of gravitational waves from a black hole merger. The signal had traveled for about 1.3 billion years before passing through Earth. It came from two black holes with masses of roughly a few dozen suns. By the time their wave reached us, the event itself was ancient history, but the information was still present in the stretching and squeezing of space. The distortion measured by LIGO was extraordinarily small, far smaller than the width of an atomic nucleus over the length of the detector arms. Yet, hidden in that tiny motion was a complete story, in spiral, merger, and ring down. The waveform revealed the masses of the black holes, the approximate distance, and the mass of the final remnant. A fraction of the system's mass energy had gone into gravitational waves. This changed astronomy. Before gravitational wave detection, black holes were studied mainly through light and motion, X-rays, stellar orbits, accretion disks, lensing, and radio images. Gravitational waves let us study black holes through their dynamics directly. A pair of black holes can merge in darkness with little or no electromagnetic signal and still announce itself through space-time. The detector network now includes LIGO, Virgo, and Kygra. Multiple detectors help confirm signals and improve localization on the sky. Each new event adds to a growing population of black holes. Some are similar to what stellar evolution predicts. Others raise interesting questions about how such systems form, how massive the original stars were, whether the black holes formed in isolation or in dense clusters, and how often mergers happen across cosmic history. Gravitational waves also test general relativity. The shape of the signal can be compared with predictions from Einstein's theory. The ring down of the final black hole can be used to ask whether the remnant behaves like a Kerr black hole. These tests are difficult, but they are powerful because they probe gravity where it is strong, fast, and highly dynamic. A black hole merger is brief in the detector, but vast in meaning. Two invisible objects spiral together. Space-time ripples outward. More than 1 billion years later, a human instrument records a faint pattern. From that pattern, we reconstruct an event no telescope needed to see. The universe moves, and geometry carries the memory. Now stay with the gravitational wave signal for a little longer. Imagine the waveform arriving on Earth as a tiny pattern in the detector, a brief rise and fall from an event long gone. What can such a small trace tell us about the lives of stars? A single stellar mass black hole can form when a massive star collapses. But a binary black hole merger requires a larger history. Two massive stars may form together, evolve together, survive supernovae, and leave behind two compact remnants in orbit. Or black holes may meet later in a dense environment such as a star cluster, where close encounters can create new pairs. Each pathway leaves clues. The masses of the black holes matter. Their spins matter. The orientation of those spins can suggest whether the objects evolved together or were assembled dynamically. The rate of mergers across cosmic time can reveal how common different formation channels are. A gravitational wave signal may last only seconds in the most sensitive part of the detector, but it can carry information about millions or billions of years of stellar evolution. Some detections also touch the boundary between neutron stars and black holes. Why does that boundary matter? Because neutron stars are supported by quantum and nuclear physics, while black holes form when collapse goes beyond that support. The exact mass at which a neutron star must become a black hole is still an active question, because it depends on the behavior of ultra-dense matter. When gravitational wave observatories detect compact objects near this boundary, the signals help physicists narrow the possibilities. A compact object of a certain mass may be a heavy neutron star, a light black hole, or something that forces scientists to refine their models. The death of a star does not only tell us about stars. It tells us about matter under pressure far beyond anything on Earth. Mergers can also create larger black holes. After two black holes combine, the remnant is more massive than either parent, though not as massive as the simple sum, because some energy has been radiated away as gravitational waves. The final object often spins rapidly. In dense environments, such remnants might merge again, building heavier black holes step by step. This is one possible route toward some intermediate mass black holes. The waveform itself has a structure, almost like chapters in a physical story. The inspiral is the gradual tightening of the orbit. The merger is the moment when the horizons combine. The ringdown is the final settling of the remnant. Each phase speaks differently. The inspiral reveals masses and orbital motion. The merger probes strong gravity at its most non-linear. The ringdown reveals the final black hole's properties. It is tempting to call gravitational waves the sound of black holes. The comparison can be useful if we remember its limits. Detectors do not hear air pressure. They measure changes in distance caused by space-time strain. Scientists can convert the frequency of a signal into audio for human ears, but the wave itself is geometry, not sound. The universe is not making noise in the ordinary sense. It is changing shape. The first detection was so important because it confirmed several things at once. Stellar mass black hole binaries exist. They can merge within the age of the universe. Gravitational waves are real and detectable. General relativity works remarkably well in a strong field, fast-moving regime. A new observational field opened in a single signal. Since then, each event has added texture. Some mergers are heavier. Some are farther away. Some involve possible neutron stars. Some have uncertain origins. The catalog grows, and with it grows the picture of a universe where compact objects are not rare curiosities, but active participants in cosmic history. The calm lesson is that black holes are not always solitary endings. They can be members of pairs, products of stellar families, participants in clusters, and builders of larger remnants. They do not merely sit in space. They orbit, spiral, merge, and leave waves moving outward long after the horizons have become one. Now imagine returning to a single horizon and asking a very different kind of question. If a black hole hides whatever falls in, can it still have a temperature? Can it have entropy? Can something that seems so dark belong to the physics of heat? This connection was surprising because black holes first appeared to remove things from view. Thermodynamics is usually about heat flowing, systems changing, and disorder increasing. Yet black holes forced physicists to notice a deep resemblance between horizons and entropy. In classical general relativity, the area of a black hole event horizon tends not to decrease in ordinary processes. If matter falls in, the horizon grows. If two black holes merge, the area of the final horizon is expected to be at least as large as the total area in the appropriate sense. This behavior resembles the second law of thermodynamics, where entropy tends not to decrease. Jacob Bekenstein proposed that black holes should have entropy. Stephen Hawking's work strengthened the connection and showed that black holes also have a temperature in quantum theory. The result is one of the most profound ideas in modern physics. The entropy of a black hole is related to the area of its horizon, not the volume inside. Why is that so strange? In ordinary systems, if you give particles more volume, you often increase the number of possible arrangements. Entropy is connected to how many microscopic states could produce the same large-scale appearance. For a black hole, the relevant quantity scales with area. The boundary seems to encode something about the hidden possibilities. This is not merely poetic. It is a mathematical clue. Black hole entropy suggests that information, geometry, and gravity are connected in a way deeper than ordinary intuition expects. A horizon is not a material surface, yet its area behaves as if it counts something. The edge that light cannot escape becomes a measure of hidden information. Hawking radiation adds another layer. When quantum field theory is considered near a horizon, black holes are predicted to emit radiation with a temperature. For astrophysical black holes, this radiation is extraordinarily weak. It has not been directly observed from known stellar mass or supermassive black holes. A large black hole is far colder than the cosmic microwave background today, so it is not evaporating in any measurable astronomical way we can watch with telescopes. Still, the theoretical result changed everything. In classical physics, a black hole can only grow in ordinary circumstances. In quantum theory, it can very slowly lose mass by emitting Hawking radiation. Over unimaginably long timescales, a black hole could evaporate. For large black holes, those timescales are vastly longer than the current age of the universe. The importance of Hawking radiation is not that we expect to see Sagittarius, a star, disappear. We do not. The importance is that it forces gravity, quantum mechanics, and thermodynamics into the same problem. The horizon becomes a place where our theories overlap, and their overlap is not fully understood. Black hole thermodynamics turns darkness into a kind of equation. Area behaves like entropy. Surface gravity is related to temperature. Mass is related to energy. The horizon becomes part of the bookkeeping of nature. This is astonishing because a black hole seems simple from the outside. It can be described by mass, spin, and perhaps charge. Yet that simplicity hides an enormous number of possible internal histories. Here, wonder follows the science naturally. The universe has made objects that are both physical and conceptual. They pull in gas, bend light, merge, and shake space-time. At the same time, they teach us that information may be woven into geometry. A black hole is not only an astronomical object. It is a question written as a horizon. Now the horizon asks its deepest question. Imagine throwing a book, a star, or a cloud of particles into a black hole. From outside, the details seem to vanish. But in quantum mechanics, information is not supposed to be destroyed. So, where does the information go? The information paradox begins with this tension. Quantum mechanics strongly suggests that information is preserved. If you know the complete state of a system, the laws should allow that state to evolve without truly erasing information. But classical black holes hide whatever falls in behind an event horizon. Hawking radiation, in its original simple form, appeared thermal, as if it carried little or no detailed information about what formed the black hole. The question is easy to ask and hard to answer. If a black hole evaporates completely and the outgoing radiation carries no information, then quantum mechanics seems to be violated. If information escapes, then we need to understand how it is encoded without allowing anything to travel outward from inside the horizon in a forbidden way. If information remains in some remnant, that raises other problems. Every path is difficult. This is why the information paradox has lasted so long. It is not a minor technical puzzle. It sits at the intersection of gravity, quantum theory, thermodynamics, and the meaning of space-time. It asks whether the smooth horizon of general relativity and the information-preserving structure of quantum mechanics can both be right as usually understood. Several ideas have been proposed. The Page curve describes how the entropy of Hawking radiation might behave if information is ultimately preserved. Modern calculations involving islands suggest that, in certain theoretical settings, information recovery can be consistent with gravity and quantum mechanics. The holographic principle suggests that information in a gravitational system may be encoded in a lower dimensional boundary description. These are powerful ideas, but they are advanced theoretical territory and should not be presented as simple, settled facts about every real black hole in the sky. Firewalls are another proposed idea. They arose from arguments about whether the horizon must become violent in order to preserve quantum information. But firewalls are not established observational features. We should not say that every black hole definitely has one. The honest statement is that they are part of an active debate about how to reconcile the smooth horizon with quantum information. The no-hair idea belongs in this discussion too. In classical general relativity, a settled black hole can be described from the outside by only a small number of properties: mass, spin, and charge. Astrophysical black holes are expected to be nearly neutral because surrounding plasma tends to cancel large charge quickly. So, in practice, mass and spin dominate. The rich details of the collapsing star or merging system seem to disappear from the external description. That simplicity is beautiful and troubling. A star has layers, elements, magnetic fields, turbulence, history, and structure. A black hole formed from that star can settle into something described by very few numbers. Where did the detailed information go? Is it hidden in subtle correlations in radiation, encoded at the horizon, preserved in a deeper quantum description of space-time? These are not questions for atmosphere alone. They are technical questions that shape modern theoretical physics. The safest way to narrate this frontier is with humility. black holes expose a disagreement between our best frameworks. General relativity describes space-time and gravity with extraordinary success. Quantum mechanics describes matter, fields, and information with extraordinary success. A black hole asks both theories to speak at once. Their combined answer is still incomplete. That incompleteness is not a failure of science. It is how science finds its next doorway. The event horizon hides the interior from direct view, but it does not silence the questions. Around that boundary, physicists have discovered links between entropy, area, temperature, and information. The black hole remains dark, yet it has illuminated one of the deepest problems in nature. Now widen the view until a whole galaxy fills the scene. A black hole may have a horizon far smaller than its host galaxy, yet the region around it can send energy outward across enormous distances. How can something so compact influence something so vast? The answer is not the horizon acting alone. It is the material falling toward it. When gas accretes onto a central, supermassive black hole, it can produce radiation, winds, and jets. Those outflows can heat surrounding gas, stir it, or push some of it away. Since stars form from cold gas, changing the gas can affect future star formation. This process is often called feedback. In some galaxies, feedback may help regulate growth. In others, the relationship is more complicated. It is tempting to say that black holes control galaxies, but that is too strong. Galaxies are shaped by dark matter, gas flows, star formation, mergers, supernova, magnetic fields, and environment. Supermassive black holes are one part of a larger system, but when they are actively feeding, they can be a powerful part. Quasars show the extreme case. Imagine looking into the early universe and seeing a galactic center so bright it outshines the stars around it. The central black hole remains dark at the horizon, but the accretion disk converts gravitational energy into radiation with extraordinary efficiency. A feeding black hole can make a galaxy's center visible across cosmic distances. Now imagine a single star passing too close to a supermassive black hole. What happens when the difference in gravity across the star becomes stronger than the star's own self-gravity? This is a tidal disruption event. The star is stretched into streams of gas. Some material may escape, while some falls back toward the black hole and heats up, producing a temporary flare. For astronomers, the event is a beacon. For the star, it is the end of its structure. The same basic tidal physics appears at many scales. Near a stellar mass black hole, a human-sized object could be stretched by the difference in gravity across its length. Near a supermassive black hole, an entire star can be disrupted if it passes within the tidal radius. Gravity does not need to touch like a solid hand. It only needs to vary across distance. Black holes can also live quietly for long periods. A supermassive black hole with little gas nearby may be faint. It still has mass. It still shapes nearby orbits. But without a supply of infalling material, it may not produce a bright accretion disk. Activity depends on fuel. A black hole can be a dormant center in one era and an active engine in another. This gives galaxies a changing history. The central black hole may grow during periods of gas inflow, perhaps triggered by mergers or instabilities. It may release energy that changes surrounding gas. It may enter quieter phases. Stars continue to orbit. Gas cools or heats. The galaxy evolves through many processes at once. The lesson is not that black holes are villains at the centers of galaxies. They are physical participants. They convert gravitational energy into radiation and motion. They can tear apart unlucky stars, launch jets, and heat gas. They can also sit quietly, known mainly by the orbits around them. Their influence depends on context. This is a calmer and more accurate picture. A black hole is not always devouring everything nearby. Much of a galaxy can orbit safely at great distances. The Milky Way is not being consumed by Sagittarius, a star. But near the center, where gas and stars pass close enough, the compact mass matters deeply. The horizon is small. The consequences can be vast. As the journey reaches the frontier, it is worth slowing down. Some of the most interesting black hole ideas remain speculative, and the word speculative is important. It does not mean foolish. It means not confirmed. Science needs ideas at the edge, but it also needs labels that keep possibility separate from observation. Primordial black holes are one example. Imagine the very early universe, when density was not perfectly smooth. If some regions were dense enough, they might have collapsed directly into black holes without ever becoming stars. Such objects would be different from stellar black holes, and depending on their mass, they might have possible connections to dark matter, gravitational waves, or early cosmic structure. But no primordial black hole population has been confirmed. Any claim about their abundance needs strong evidence. Wormholes are another idea often linked to black holes in popular imagination. A wormhole is a hypothetical connection between different regions of space-time. But the black holes we observe through stellar motion, accretion, EHT images, and gravitational waves are not known to be traversable tunnels. They are horizons formed by gravity. The science fiction doorway is not the same as the astrophysical object. White holes appear in some mathematical discussions as time-reversed versions of black holes, regions that things could leave but not enter. No confirmed astrophysical object has been identified as a white hole. They are interesting in theory, but they should not be presented as ordinary cosmic objects waiting to be discovered tomorrow. The holographic principle is more subtle. It is motivated in part by black hole entropy, especially the fact that entropy scales with horizon area. In certain theoretical frameworks, a gravitational system can be related to a lower dimensional boundary theory. This has produced deep insights in theoretical physics, but it should be explained carefully. It does not mean the universe is simply a projected movie in the everyday sense. It means information, geometry, and dimensionality may be related in ways ordinary intuition does not capture. The page curve and island ideas also belong to the frontier. They are part of modern attempts to understand how black hole evaporation could preserve information. In some theoretical settings, they provide a way to calculate radiation entropy consistent with unitarity. But this is not the same as saying telescopes have watched information come out of an evaporating astrophysical black hole. The distinction protects the science. Firewalls are another debated proposal. They ask whether the horizon might become a high-energy region for an infalling observer if certain assumptions about quantum information are maintained. This is not an established observational fact. It is a sign of how sharp the paradox becomes when our theories are forced together. So, how should we travel through these ideas without losing the ground beneath us? The answer is to separate the established from the possible. We can confidently explain event horizons, accretion disks, gravitational lensing, time dilation, tidal forces, EHT shadows, and gravitational waves. We can also say that black holes raise unresolved questions about quantum gravity and information. The transition from known to unknown should be clear. Wonder does not require overstatement. In fact, the real wonder becomes stronger when the boundaries are honest. Confirmed black holes are already extraordinary. We have measured stars orbiting dark masses, imaged shadow structures around horizons, and detected ripples from mergers across the universe. The speculative frontier adds depth, but it does not need to pretend to be settled. The best way to approach these ideas is with a calm sentence. This is where physics is still working. Around black holes, certainty and mystery meet at the same boundary. The horizon hides, and the questions gather around it. Before the journey turns homeward, it is worth clearing away a few images that can mislead as easily as they inspire. Black holes are surrounded by myths. Which ones should we leave behind? The first myth is that black holes roam the universe, swallowing everything in their path. They do not. Gravity still follows the rules of mass and distance. A black hole with the mass of the Sun would affect Earth from the Sun's distance almost the same way the Sun does gravitationally. The difference is not reach. The difference is compactness. The second myth is that the event horizon is a physical surface. It is not. There is no solid shell at the horizon, no crust, no material skin. It is a boundary in space-time. Outside it, future-directed paths can still reach distant space. Inside it, they cannot. This makes the horizon more subtle than a surface and more final than a wall. The third myth is that the EHT photographed the event horizon directly. The EHT imaged emission around black holes and the shadow structure produced by extreme gravity. The horizon helps create that shadow, but the image is not a close-up of a material edge. It is a view of light near the point where escape becomes impossible. The fourth myth is that black holes destroy energy. In ordinary accretion, energy is transformed and redistributed. Matter falling toward a black hole can radiate energy from the accretion disk. Some energy may go into jets or outflows. Some becomes part of the black hole's mass and spin. Conservation laws still matter. Black holes do not give permission to abandon physics. The fifth myth is that black holes are empty holes in a fabric. The fabric analogy can help people picture curvature, but it can also create confusion. Space-time is not a rubber sheet embedded in a higher room. A black hole is not a drain punched through a surface. It is a solution of gravitational physics, a region where curvature and causal structure produce an event horizon. The sixth myth is that falling into a black hole looks the same for everyone. It does not. A distant observer may see an infalling object slow, redden, and fade near the horizon. The infalling object in its own proper time can cross the boundary. Relativity makes viewpoint part of the description. There is no single universal clock narrating the event from above. The seventh myth is that all black holes are the same size. In reality, mass changes scale enormously. A stellar mass black hole may have a horizon measured in kilometers or tens of kilometers. A supermassive black hole can have a horizon larger than planetary orbits. The same concept, an event horizon, can appear in objects separated by millions or billions of times in mass. The eighth myth is that speculative ideas are already confirmed because they sound exciting. Wormholes, white holes, some primordial black hole claims, firewalls, and the deepest versions of holography belong to the frontier. They should be discussed with interest, not treated as established observations. Scientific wonder is strongest when it can tell the difference between evidence and possibility. Correcting myths does not make black holes less fascinating. It makes them clearer. The real physics is already strange enough. Time dilation, gravitational redshift, photon orbits, frame dragging, accretion disks, jets, mergers, entropy, and information puzzles. These are not decorations added to darkness. They are the subject itself. When the myths fall away, the black hole becomes more elegant. It is not a monster. It is not magic. It is a boundary created by gravity, surrounded by some of the most energetic and revealing processes in the universe. The truth is quieter than the legend, but far deeper. Now imagine that the journey pauses, not near one black hole, but among all the ways scientists use them. Why do these objects occupy such a central place in modern physics? One reason is their strange simplicity. A settled black hole can be characterized from the outside by a small set of properties, especially mass and spin. Charge can exist in the equations, but real astrophysical black holes are expected to be nearly neutral because surrounding plasma tends to cancel net charge quickly. Compared with a star, this is astonishingly spare. A star has composition, temperature layers, storms, magnetic regions, fusion processes, a surface, and a history visible in its light. A black hole hides nearly all of that. The matter that formed it may have been oxygen, carbon, iron, plasma, stellar core, or merger remnant. From outside, after settling, the detailed composition no longer appears in the same way. The black hole presents mass, rotation, and gravitational influence. This simplicity is part of the no-hair idea. The phrase is informal, but the point is serious. Many details of the original object are not visible in the external classical description. The black hole compresses not just matter, but description. It takes an elaborate history and reduces what the outside universe can measure. And yet, if you look around the horizon, the environment is anything but simple. Gas can heat into plasma. Magnetic fields can twist. Jets can launch. Stars can whip around at high speed. Photons can follow curved paths that bring the far side of a disk into view. The center is simple in its external parameters. The surroundings are rich. This contrast makes black holes powerful for science. Because the theoretical object is simple, deviations can be meaningful. If observations of a shadow, a gravitational wave ring down, or stellar motion disagree with predictions, scientists can ask whether the environmental model is wrong, whether the measurement needs improvement, or whether gravity itself is showing something new. Simplicity becomes a testing ground. Black holes test general relativity because the theory makes strong predictions about their behavior. The size of a shadow, the precession of stellar orbits, the shape of gravitational waves, the ring-down frequencies after a merger, and the motion of matter near the innermost stable orbits all connect to space-time geometry. Each observation becomes a question asked of Einstein's theory. They also test plasma physics. Accretion disks are not smooth, glowing circles. They are turbulent, magnetized, relativistic flows. Understanding them requires magnetohydrodynamics, radiation transport, particle acceleration, and sometimes radiation pressure. The visible drama around a black hole is produced by matter under conditions difficult to recreate on Earth. They test high-energy astrophysics. Jets from active galactic nuclei can accelerate particles and carry energy across huge distances. X-ray binaries can switch states as accretion changes. Tidal disruption events can reveal how stars are torn apart and how gas returns toward the black hole. Each system is a natural experiment. They test quantum theory indirectly through entropy, Hawking radiation, and the information paradox. Even if we cannot observe Hawking radiation from known large black holes, the theoretical connection forces physicists to ask what a horizon means in quantum terms. The object in the sky becomes connected to equations about information and microscopic states. This is why black holes are not only endpoints of stellar collapse. They are laboratories built by nature. They combine gravity, motion, heat, magnetism, radiation, and information. They are dark at the center, but scientifically luminous around the edges. If we step back from the horizon, the whole story becomes a story of transformation. What changes form as a black hole is born, feeds, merges, and reveals itself. A massive star begins as gas in a cloud. Gravity gathers it. Fusion lights it. For a time, the star holds itself in balance, turning mass into energy and sending light into space. Then the fuel changes, the core evolves, and the balance fails. In some stars, the end becomes a supernova. The outer layers are thrown outward, carrying elements into the galaxy. Oxygen, carbon, silicon, iron, and many heavier elements become part of interstellar material. Future stars and planets may form from that enriched gas. Stellar death is not only destruction, it is distribution. At the center, the remnant faces the final question of pressure and gravity. If matter can resist, a neutron star may remain. If gravity wins beyond that resistance, a black hole forms. The object that was once a shining core becomes a horizon. The star's history does not disappear completely. Its mass and spin remain. Its surrounding debris may glow. Its effect on nearby matter continues. But the interior is no longer available to the outside universe. This transformation continues in other ways. Gas falling toward a black hole becomes radiation. Orbital motion becomes heat. Magnetic fields and plasma can become jets. Two compact objects orbiting together become gravitational waves and a larger remnant. A galactic center can turn infalling matter into light visible across cosmic distance. Even the absence of light becomes information. A shadow in an EHT image tells us about curved photon paths. A missing visible companion in an X-ray binary tells us about compact mass. A star's orbit around Sagittarius. A star tells us about an unseen central object. A tiny strain in a detector tells us about horizons merging long ago. Black holes transform invisibility into evidence. There is also a transformation in human understanding. The idea began in mathematics and theory, with solutions to equations and questions about escape velocity. Over time, black holes moved from speculation into observation. We found compact X-ray sources. We measured stellar orbits around galactic centers. We detected gravitational waves. We imaged shadow structures. The impossible became part of the catalog of nature. This does not mean black holes are fully understood. The deepest interior remains hidden. Quantum gravity remains unfinished. Information remains a frontier problem. The formation of the earliest supermassive black holes still raises questions. Intermediate mass black holes remain an active search. The details of jets and accretion still challenge simulations. The subject is mature and unfinished at the same time. That combination is part of its beauty. Some facts are solid enough to teach with confidence. Others are open enough to invite humility. The event horizon is a defining concept. Accretion disks can shine. Gravitational waves have been detected. EHT rings match black hole expectations. Hawking radiation for astrophysical black holes remains a theoretical prediction too weak to observe directly. Primordial black holes remain hypothetical. Each statement has its proper weight. A good black hole story should preserve those weights. It should not flatten everything into certainty, and it should not dissolve everything into mystery. The known science gives the narrative strength. The unknown gives it depth. So the black hole becomes more than an ending. It is a converter of forms, star to remnant, orbit to wave, gas to light, area to entropy, darkness to measurement, certainty to deeper questions. In that transformation, we glimpse one of the universe's quiet habits. It changes what exists, but it rarely wastes what can still speak. By now, as the journey begins to turn outward, the black hole has changed shape in our imagination. It is not a tunnel punched through space. It is not a wandering vacuum cleaner. It is not a solid black planet. So, what is it, after everything we have seen? It is a region where gravity is geometry, where the future tilts inward, where light can orbit, where time can stretch, and where matter can become brilliant just before it disappears from view. The event horizon is the central idea. It is not a material surface, yet it is more final than any wall. It marks the boundary beyond which no signal can return to distant space. Around that boundary, the universe becomes expressive. Gas forms accretion disks and heats until it shines. Magnetic fields help shape jets. Light bends around the dark center and forms rings and shadows. Stars reveal hidden mass through their orbits. Gravitational waves carry the memory of mergers. Thermodynamics turns horizon area into a clue about entropy. Quantum theory asks whether information is ever truly lost. The black hole is therefore both an object and a question. As an object, it can be measured. It can have mass, spin, a shadow, a merger signal, an accretion disk, and a place in a galaxy. As a question, it asks what space-time is, what information means, and what happens when our best theories meet at their limits. Consider the scale of what we have learned. We know that the Milky Way contains a central black hole because stars near the galactic center move around an unseen compact mass. We know that M87 star has a shadow structure because radio telescopes across Earth work together as a planet-sized instrument. We know that black holes merge because gravitational wave detectors have measured the strain of space-time itself. These are not guesses. They are achievements of observation. At the same time, black holes keep some secrets. The interior cannot send us a message once it is behind the horizon. The final nature of the singularity, if that word remains correct in quantum gravity, is unknown. The full solution to the information paradox is still debated. Some ideas at the frontier may survive. Others may fade. Science advances by sorting them with evidence and mathematics. This balance between knowledge and mystery is what makes black holes so enduring. They are not vague symbols of darkness. They are precise enough to calculate and strange enough to humble calculation. They are among the cleanest predictions of general relativity and among the strongest reasons to seek a deeper theory. For a listener at night, this can be a calming thought. The universe is not required to be simple in order to be understandable. It can be layered. It can give us partial answers that are real while still holding deeper questions open. A black hole does not invite panic. It invites attention. It asks us to follow the evidence carefully and let wonder arrive after understanding. The darkest objects in astronomy have taught us how to see more deeply. They turned invisible mass into measurable motion. They turned silence into gravitational waves. They turned the absence of escaping light into a visible shadow. They showed that something can be hidden completely and still leave evidence everywhere around it. That is the quiet power of the black hole. It keeps its horizon, but it cannot hide its influence. As this journey comes to its close, imagine turning away from the horizon and looking back across the path we have followed. The black hole began as a question about gravity, but not gravity as a simple downward pull. It began with space-time responding to mass and energy. It began with the idea that motion follows geometry, and that geometry can become so curved that escape is no longer part of the future. From massive stars, black holes inherit the drama of stellar life. A star burns, balances, builds heavy elements, and finally reaches a core that can no longer support itself. The collapse may scatter enriched material into space, while the center becomes a compact remnant. If pressure fails completely, a horizon forms. The bright life of the star leaves behind a dark boundary. From accretion, black holes inherit brilliance. Gas spirals inward, heats and shines. Quasars can outshine galaxies. Jets can reach across intergalactic distances. The horizon remains dark, but the region around it can become one of the most energetic places in the cosmos. Darkness and radiance belong to the same system. From relativity, black holes inherit strangeness. Time runs differently near them. Light bends around them. Distant observers and falling observers describe the horizon in different ways. Rotating black holes drag space-time, create ergospheres, and may help power cosmic engines. The ordinary instincts of daily life no longer guide us well near such gravity. From astronomy, black holes inherit evidence. We see stars orbiting Sagittarius A star. We see the shadow structure of M87 star and the Milky Way's central black hole through the Event Horizon Telescope. We see X-rays from accretion systems. We see gravitational lensing. We detect gravitational waves from mergers. The horizon emits no ordinary light, but the universe has found many ways to reveal its presence. From thermodynamics and quantum theory, black holes inherit mystery. Horizon area behaves like entropy. Hawking radiation suggests that black holes have a temperature, though the effect is far too weak to observe directly from known large black holes. The information paradox remains one of the deepest questions in theoretical physics. At the horizon, our understanding is powerful, but not complete. And from the speculative frontier, black holes inherit caution. Primordial black holes remain hypothetical. Wormholes are not ordinary observed black holes. White holes are not confirmed astrophysical objects. Firewalls are debated ideas, not established features. Holography is profound, but not a simple movie screen metaphor. Good science keeps its labels clear. What remains is already extraordinary. A black hole is a boundary in the possible paths of the universe. It is a place where mass has shaped space-time so strongly that outward motion can lose its future. It can be born from a star, grow in a galaxy, merge with another horizon, and leave waves crossing the cosmos for billions of years. It is natural to think of black holes as endings. They are the end of escape for anything crossing the horizon. They may be the final state of massive stellar cores. They hide information from ordinary view, but they are also beginnings. Beginnings of jets, flares, gravitational waves, theoretical revolutions, and new ways of observing the universe. So when we look toward a black hole, we are not looking only at darkness. We are looking at the edge of explanation. Around that edge, light bends, clocks disagree, space rotates, matter shines, and the laws of physics reveal both their power and their unfinished questions. The horizon keeps its secrets, but the universe around it keeps speaking. And for now, that is enough to follow. The glow around the unseen, the motion around the hidden, and the strange calm of a boundary where every outward path has quietly disappeared.